One of the reasons I really want to emphasize these iterators in Mathematica is because we can use them for things other than just making lists using the table command. So as an example, let me remind you how we use iterators with this table command. Say I do table I squared I from 1 to 5. So that gives me 1, 4, 9, 16, 25. And basically what it means is go through all these values of I, plug them each into this expression, and put it into a list. And I can do something really similar using sum instead of table. So what did this do? Well, it basically took this list up here and added them all up. That's how sum works. It says, go through each of these values that's indicated over here, plug it into this expression, and then instead of putting them in a list like I do up here, the sum command says add them up. So just to convince you that they're the same, I could call this one my list, and then if I do total my list, I get the same answer. And an easy mistake to make would be trying to do sum of my list, but this isn't going to work. It says that it's expecting a second argument here. I'm supposed to have some comma and then some iterator over here on the right-hand side. So if you want to just add up everything in a list, you use total. You don't use sum. So let me do an easier version. Say I do sum of I for I from 1 to 5. Okay, this is 1 plus 2 plus 3 plus 4 plus 5. So this is less interesting than what we just did. But here's a cool thing about Mathematica, and this is related to the fact that it treats everything symbolically. It doesn't make a decimal approximation until it absolutely has to. So as an example, I could do sum of this random variable a. So a, you can tell I haven't defined it because it's in blue. I didn't mean anything precise by random variable. I just meant some name I chose randomly. And if I evaluate this, I got 5a. Why did I get 5a? Well, think about it. I get a for I equals 1, a for I equals 2, all the way up to a for I equals 5. I add them up. Total, I get 5a. Okay, here's back to sum of I for I from 1 to 5. And one of the other symbolic things that I can do, instead of saying go up to 5, I can say go up to some variable n, which I haven't defined. And I think this is really amazing in Mathematica that this actually works. So if you've seen it before, like this is a common Math 13 proof, if you add up the numbers 1 up to n, what's the formula for it? One way to prove it is using induction. N times n plus 1 over 2 is a formula for it. And maybe you've seen them before. There are also formulas for sums of squares. Okay, they're more complicated, but here it is. If I wanted in a different format, I could say expand this. And maybe you like this one better. Maybe you like the factored version better. Okay, I'll just go back to the simpler one. But expand is what you can use if you want to get rid of some of these parentheses. Okay, and I can do the same thing for I cubed, same thing for I to the 4th. So let's go back to I cubed. So this is saying that if I add up the cubes, 1 cubed, 2 cubed, all the way up to n cubed, then there's this formula for it that doesn't involve any sigma notation. Okay, just this simple, what's called a closed expression for this sum, 1 cubed, 2 cubed, all the way up to n cubed. Another thing I can do, say I do 1 over I squared for I from 1 to 5. Okay, that's 1 over 1 squared plus 1 over 2 squared all the way up to plus 1 over 5 squared. Okay, 1 over 25. That might not seem very interesting, but here's another cool thing that Mathematica can do. I can replace this 5 by infinity. And I don't know if you've seen that formula before, but a formula, crazy formula for 1 over 1 squared plus 1 over 2 squared going on forever. A closed formula for that is pi squared over 6. Let me do one more example of how Mathematica works with expressions symbolically. And there's a function built into Mathematica called solve. Probably works basically the way you expect. So let me start it out by making a little mistake, but a common mistake. Say I want to solve x squared equals 2, and I want to solve it for x. So it gives me an error. It says tag power in x squared is protected. So can you predict what error I made here? Here, what's a common error in computer programming? I wrote equals when I should have written equals equals. Okay, I wasn't trying to set x squared to have the value 2. I was trying to ask true or false x squared is equal to 2. And there you can see, don't worry so much about the brackets, but x is negative square root of 2 or x is positive square root of 2. That's what I get when I try to solve this. So far that's not what I meant by symbolic programming, but let me show you an example. Say I do a times x squared plus b times x plus c. And say I want to solve that is equal to 0 for x. So probably this looks familiar to you. This is the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac, whole thing over 2a. And you probably knew that this existed, but did you also know a similar one exists for cubics? So ax cubed plus bx squared plus c times x plus d. It's a lot more complicated, but there you go. There's an expression in terms of the coefficients, a, b, c, and d, for the zeros of this cubic equation. Okay, there's a similar but more complicated still formula for quartics for degree 4. And then if you take Math 120C, you'll see at least a sketch of a proof that there doesn't exist a formula like this for quintics for degree 5 or higher. And so what did I mean when I said that this is treating things symbolically? Well, I mean that it's finding an answer in terms of the symbols for the first coefficient, the second coefficient, and so on. So there's no decimal approximation or numerical approximation going on in this computation by Mathematica.